All right, here we go. We're talking about the Wronskian, which sounds like a mythological creature. Turns out it's even better than that because it's related to math, right? So, Wronskian is named after a Polish mathematician of Wronski, okay, who came up with this idea. And the whole idea is basically, how do I determine if functions are linearly independent, okay? So here's the whole idea behind the whole thing. So the definition is we say that functions, let's say f1 and f2, are linearly independent. Okay, so that's what we're defining, is linearly independent, provided the equation given by c1 f1 of t plus c2 f2 of t equals 0 has only the trivial solution given by c1 equals c2 equals 0. Okay? So that seems kind of weird. I just give you two arbitrary functions, say sine of t and cosine of t, and I say, are they linearly independent? Well, then I would look at c1 sine of t plus c2 cosine of t and say, are c1 and c2 equal to 0? Well, that's a hard question to answer because what we think about is this as one equation in the two unknowns, c1 and c2. Okay, so that's not super helpful. When I have one equation and two unknowns, I'd like to have two equations and two unknowns to be able to try and solve. Okay, so here's what we can do. So if f1 and f2 are differentiable, just meaning their derivative exists, okay, then, well, I can turn this into two equations. Okay, and what are those two equations? Now, I'm going to omit putting the parentheses of t, just to simplify notation a little bit, but technically f1 is a function of t. So what can I do? If I take this equation right here, and I simply differentiate it with respect to the independent variable t, then what am I going to get? Well, the first equation will be c1 f1 plus c2 f2 equals 0. But if I differentiate, I'm going to get c1 f1 prime plus c2 f2 prime also equals 0. Again, that's if f1 and f2 are differentiable. Well, we're doing this in the context of ODEs, and so if f1 and f2 are solutions to an ODE, well then they're going to be differentiable by definition. Okay? But now I can see this as a system of equations in the variables c1 and c2. So I can write a matrix equation based on this. Okay? So that's telling me I can write this as what? Some matrix, which is given by f1, f2, f1 prime, f2 prime, times c1, c2 equals 0, 0. Okay, just as a matrix vector equation. All right, so what does that mean? Well, when does this thing, we're looking at linearly independent. Okay, so linearly independent is saying I want c1 and c2 to be equal to 0. So you kind of have to put on your linear algebra hat a little bit and go back to saying, when do systems of equations, okay, if you want to think about this written in matrix form as like ax equals 0, okay, where a is this matrix, x is this variable column vector, and 0 is just this 0 column vector. If you want to think about it that way, that's fine. But think about it from a linear algebra standpoint. C1, C2 is the unique solution to this, provided what? Well, provided that this matrix is invertible. Okay, so when is this matrix invertible? Well, this matrix is invertible. It's square. It has to be in order to be invertible. So this matrix is invertible provided its determinant is non-zero. Well, its determinant is what we call the Wronskian. Okay, so here's my definition. So the Wronskian of f1 and f2 is, so some people use different notation for this. I personally like the following. I like to put a w and then put in brackets the functions involved. So I put f1, f2. Now this is presumably going to be a function of t, okay? And that thing is going to be equal to the following. So let me get that out of the way. This will be equal to the determinant of f1 here, f2 here, f1 prime, f2 prime, okay? Which you can work out. It's a 2 by 2 determinant. So if you want to work this out in gory detail, it's just what? f1, f2 prime. So F1, F2 prime minus what? F2, F1 prime. Remember, it's this guy times this guy minus this guy times this guy. That's how determinants work. If you need a refresher on that, go back and see my video on linear algebra on how to compute determinants of square matrices. Okay? So that's what the corresponding Wronskian is. And the beautiful fact, okay, that we're going to take advantage of is, look, the determinant of this matrix is the Wronskian. Now, we just said that C1, C2 equals 0, 0 is the only solution, the unique solution, provided the determinant of this matrix is non-zero, i.e. the Wronskian is non-zero. Okay? So we could, alternatively, we could say F1 and F2 are linearly independent, provided the Wronskian of F1, F2 is not 0. Okay? Now, one thing that I need to be abundantly clear with is, look, the Wronskian is a function of t, okay? So let's suppose I got this Wronskian, maybe as just an example, maybe I get this as like t plus 1, something like that, okay? What I mean by this is that it's not equal to 0. I should really put like 3 bars here to say it's not identically equal to 0, meaning that this is not the 0 function, okay? I don't necessarily care that t equals -1. We'll make this equal to 0. What I'm saying is you're not allowed to play with values of t. You're not allowed to plug in values of t. I'm saying this thing as a determinant, as the determinant of a matrix, okay, cannot be identically equal to 0, okay? So if the Wronskian is not identically equal to 0, it is not the 0 function, then we say that F1 and F2 are linearly independent functions, and we don't have to worry about looking at this corresponding linear combination like we did when we were looking at vectors in like R2, R3, and Gaussian elimination came into play. Okay? So the Wronskian kind of bails us out for determining when F1 and F2 are linearly independent. Again, go and check out all of my linear algebra videos on that front to remind yourself about linear independence, matrices, and determinants. So there you have it. F1 and F2 are linearly independent when the Wronskian is non-zero.